All right, we're going to switch gears a little bit. Next up, we're very fortunate to have Yashar Hezaveh, who is an assistant professor of physics at the University of Montreal and the Canada Research Chair in Astrophysical Data Analysis and Machine Learning. Yashar earned his PhD from McGill before joining KIPAC as a Hubble Fellow in 2013. Yashar has also spent time at the Center for Computational Astrophysics at the Flatiron Institute in New York before starting his faculty position. And we are delighted to have you here today.
It's really a great pleasure to be back here after so many years. Thank you. So as most of you know, I have been in Montreal for the past 4 years. And so these are some of the people that make it really fun to be there. And oh, maybe I'll move that other, if you could just remove that. I want to kind of like start by telling you kind of like how, oops. Yeah, I know what that is. There you go. I want to tell you how kind of like my journey started with KIPAC. And so, one day I just woke up and I had this random email. I had never talked to Roger or anybody at Stanford before. And as it happened, that day, my wife, who was this grad student at Cambridge, was visiting Stanford. So I called Roger. I said, actually, you know what? My wife is there. She said, tell her to come have lunch with me. And I said, oh my God. I called her. I said, hope you're in a good mood because you were doing my job interview for me. So she went there, she passed. And then, a few years later, when we were both here, it was really great. Just like, we started kind of on this journey of doing machine learning together, which was really great. And looking back at it now, I only have like gratitude for the environment here, for people, for Risa, for Roger, Phil, Tom, and a lot of people, the postdocs, a lot of friends that were here. And so I'm gonna kind of cut to the chase, start talking about science. So what I do is strong gravitational lensing. So I don't know if this thing, it doesn't show there. So here, we're on the Earth. We're looking at two galaxies. One is kind of like, halfway kind of like across the universe. The other one is like really far. And as the light rays of that background galaxy, they pass near this galaxy, they get deflected, they come to us from different angles. And as a result, here on the Earth, we see multiple images of that background galaxy around this lensing galaxy. It's a little bit like looking at the images of a fish at the corner of a fish tank. You can see two different images, and that's because the light rays from the two sides are coming to us from two different angles. And so we see exactly the same thing in the sky. Here we have this lensing galaxy that is producing two different images of this background quasar. The difference is that, of course, here, the deflection is like caused by gravity instead of refraction. And quite often, these gravitational lenses in the sky, they look like this arc-like structure like you see here. And the reason for that is the geometry of lensing is this kind of like spherical kind of symmetric thing. So you can kind of reproduce images like that with the foot of a wine glass. Most people at KIPAC know this already. But I just want to make this analogy that the foot of the wine glass is basically this lensing galaxy that's distorting the image of the background source. And the candle is this, the distant galaxy whose image is being distorted. So why do we do strong lensing? What do we want from it? And so there's kind of like 3 different categories of sciences that are done with strong lensing. Either we want to study the background source or the foreground lens, or maybe we use the whole system, to study cosmology, for example. And so for the background source, typically we take advantage of lensing as a cosmic telescope because it magnifies the images of background sources. It makes them appear bigger and brighter. So it allows us to see things that are below our detection or resolution thresholds. And so, it's perhaps like, most important for example, study galaxy formation at high redshifts. For the foreground lens, we use lensing because the distortion in the images are caused by gravity, and gravity is caused by matter. So we can use it to map the distribution of matter in the lenses or along the line of sight. And it's particularly important for dark matter, for example, studying dark matter. And finally, we can use the system, statistics of lenses or time delays or things like that to study cosmology, for example, measuring H0. But no matter what we're trying to do, we always need to analyze these lenses. We always need to do this thing called lens modeling, which means that we need to infer 2 sets of kind of properties about these lenses, kind of physical things. And the first thing that I want to know is that what does the background source truly look like? We want to know what is the undistorted image of the candle. And the other one is, what is the shape of the foot of the wine glass? What is the mass distribution along? So if we know these two things, then we know everything about the system, and then we can do the science that we want to do. So a likelihood-based approach to doing that is that, I can just like have simulations. I can have a simulator that's easy. I can get a background source, a foreground lens. I propose these as models, simulate it, and I can compare that to my data using some sort of likelihood function. And then I can just propose a gajillion of these and then figure out which one of them look like my observed data. And so the distribution there is my posterior. So in theory, this is like, great, but in practice, it doesn't work really well because there are so many degeneracies. The parameter space has a lot of local minima, and it is very difficult. So, we were spending weeks and months to analyze like, one kind of simple model for a lens. And that was just like not scalable. So now we're kind of considering that big surveys like LSST and Euclid, we're discovering an order of like hundreds of thousands of strong gravitational lenses. So like 10 years ago, we discovered like in our team with SPT SMG about 50 lenses. And this was like a Nature paper doubling the number of lenses known. But 200,000 lenses is a whole like 3 orders of magnitude, more than anything we were dealing with before. So having like, 3 grad students kind of like working for 2 years and publishing the, 5 lens model is just not possible anymore. And so this kind of like motivated us here at Stanford, I go back, to start looking in the use of machine learning to speed up these calculations. And so basically the idea was very simple. We just said, hey, people are using these like CNNs for classification. What if we just take the last layer off and we just like predict the lens models? And they work so beautifully, and it was just like incredible how well they work. So we worked with this like with Phil Marshall, and we submitted it to Nature, and then the referee report came back, and then me and Laurence, we started working on this, and she was 39 weeks pregnant. And then the next day we were working on this, she's like, I have to go to the hospital. And then she said, but if we don't kind of respond to the referee report in the next 12 hours, it'll never happen. And I said, okay, like, what do you want me to do? And she said, tell them to give me the epidural so that we can work on the referee report. So we just sat there and we worked on the referee report. And then, that we went great. So, but that was just the beginning of this journey into kind of machine learning. So from that point on, we went to kind of working with Warren Morningstar, who was a grad student at that point with Roger and Risa. And so we said, hey, we're going to take this one step further. Instead of predicting some simple parameters for these lenses, can you reconstruct the whole background source? So I want to give you this like observed image, and I want to kind of have this undistorted image of the background source on a pixelated, scale. And the models were doing really, really well, because one thing that they were doing great is the learning the priors in these images implicitly. And then a few years later, in Montreal, one of our stellar graduate students, Alex Adam, has kind of taken this to another step to not only predict the background source, but the density in the foreground lenses. So here are kind of like the ground truth coming from a luster simulation, and here are the predictions for the projected density map from these machine learning models. But all of this was in the kind of context of predicting point estimate. But you cannot do science with point estimates, right? You need uncertainties. You need to understand your uncertainties. And kind of that journey started with this paper with Laurence and Risa to use the Bayesian neural networks for kind of like having a kind of estimating the posterior of the parameters of these lenses, having uncertainties, having the full posterior. And it was very promising because, it started working really well. So we just understood that this is not just some black box that you cannot do anything with it. You can actually start like, treating your inference problems, with some level of like rigor. And ever since then, a lot of my focus in Montreal has been just like based on this, kind of like, how can we use machine learning in a way that allows us to do science within a rigorous Bayesian framework that I can actually trust. If somebody comes to me and says, here's a 5 sigma detection of a Nobel Prize level something, and I use machine learning or deep learning, I need to be able to really trust that and understand that you can actually do that, not just because it ran on your simulations and it worked. That's not good enough. And so we've made a lot of progress in that. And one of the really cool things that we did was led by Ronan Leggin, who was one of the absolutely stellar PhD students in Montreal, to kind of like frame this problem in the context of likelihood-free inference and just say that if you have a neural network that is making a prediction, and it's a point prediction, a point estimate, you can take this and interpret it as a sufficient or as a statistic of the data, and then run kind of like things like, you know, ADC, like approximate Bayesian computation, or like, you know, and this thing, and actually get the posteriors out of that. And this worked really well. And then we kind of just, you know, went, you know, to other aspects. Like there's a lot of things that we need to do with machine learning if you want to apply it to big surveys like LSSD. Another problem is, for example, hierarchical Bayesian inference. So let's say that I'm not interested in the parameters of these individual lenses, but I'm interested to analyze like, you know, thousands of these and then learn about their distribution. What is the distribution of mass in the universe? What's the mass function? What's a lot of these things? So if I'm interested in the distribution there, one thing that could go wrong is that I'm not going to kind of have IID samples of these things because there's like selection issues. So my lens finder, for example, or whatever other things in the survey might have missed some of these lenses. And if I just do my inference, I'm going to get a biased distribution for the things that are there. And so historically, you know, what people do is that when they do these like MCMC runs, they would have to run thousands of simulations in the middle to account for that and then correct for that. So one thing that we did here with Ronan was to just say that we can actually learn that with our neural net. So I can get my neural net lens detector and then have another neural net that learns the selection function of these as a function of all the parameters through simulations. And then if I do that, I can show that I can actually correct for that. So here is a kind of like a, you know, toy problem where we have a distribution of these things that is kind of normal. We're predicting the parameters of this normal distribution of like thousands of lenses, but we're not observing all of them because they've been put through some lens detector. And if I just like, you know, so this star is the ground truth. And if I just do it blindly, I'm going to get the bias estimates here, the blue ones. But if I actually get this other neural network that has learned the selection function and correct for it with that, then I can get the red curves there that are basically unbiased estimates. And then finally, another kind of like thing in this thing has been the rise of the NRE, the neural ratio estimators that have become very popular, at least became very popular for some time. And again, I'm not going to go into the details of these, but one of the advantages of these NREs is that they could marginalize over a very large number of parameters and give you actual posteriors of like a small handful of parameters, which is both their pro and their con at the same time. Because the pro is that that's great. I can marginalize over like lots of nuisance parameters and get something like H naught. You know, this is the work that Ev has led. He was a master's student with Laurence. And so, you know, she can show that, you know, with like, you know, 8,000 lenses, you can train these NREs to give you a posterior estimate of H naught to, you know, less than % accuracy. The con is that at the same time, the things that they marginalized over, you don't know them anymore. So you cannot verify exactly what happened there. But, you know, I think that the best use of these is actually for forecasting complex things like LSSD. And so one of my students, Andy, who was actually this summer here for the desk meeting, is taking that to actually apply it and like for LSSD, predict like, what can you learn about dark matter substructure and the mass function? And so, you know, with NREs in terms of like forecasting for LSSD, which is really great. But okay, so what I want you guys to do now, this thing stopped working, is to, there you go, forget about everything I said. I want to switch gears. So just make some room in your head. And I want to talk about the inference of high dimensional parameters. This is a big problem in all of sciences, in everything. That, you know, if I have 10 parameters, you can put a prior on it, you can use an MCMC sampler or whatever. But when you have 400,000 parameters, like we don't know how to sample it. We don't know how to define priors on it. What is a prior in 400,000? Yeah, sure, you can put a Gaussian. That's the only thing we know how to do. And so in the past few years in machine learning, this problem has basically been almost solved. And that is really the exciting thing that I want to talk to you guys about. And so the two things I want to talk about is exactly these two things. How do we encode complex priors within a really like well-defined Bayesian, you know, framework? And then how do we sample them if we have like big things? And so by high dimensional, I mean things like an image. So an image that has, you know, 400 by 400, you know, pixels, you know, basically it has like 400 square kind of dimensions. And so you can imagine that this distribution here, kind of, this is kind of like, you know, some schematic of just like each one of these dots is an image. So our goal is to basically learn a distribution over these images. And as it turns out, learning the distribution is a lot easier if you actually learn its gradient. And again, I don't have time to go into the details of that, but now we can train machine learning models that learn that distribution from sets of images and actually learn the gradient of this distribution. And then once you have learned that gradient, which we call the score model or the score function, you can sample it using old physics of diffusion. And I know a lot of people here would know so much about that. Basically, you use exactly diffusion, Fokker-Planck equation, and all of those things to sample these things, and it's absolutely beautiful. It's a really well-defined framework for doing these things. And so now what we're going to do is that we're going to say, I'm going to throw a bunch of these examples and learn a distribution here, and I'm going to use it as my prior, add my likelihood, and then sample the posterior. So here's an example. So we're sampling the posteriors of background sources, not only a point estimate. Each one of these different things is a different posterior. And look at it, how well it works. So I can get a number 7 and lens it, and then try to reconstruct it. And if I have very good quality data, I can recover it to 7. As the quality of the data gets worse, the prior kicks in, and now you start getting galaxy-like things, because our prior is things that look like galaxies. And then we can take it one step further and just say, how about we actually learn the noise model itself? We can have complex noise that is not Gaussian. A lot of times, we just treat noise as Gaussian. So I don't have time to get into the math of this, but the point is that we get these like images of HST raw data, like the one on top, that have cosmic rays and everything. And from that, we can learn the noise model. And then when we're sampling these things with diffusion models, we can recover unbiased parameters like the ones that you see in the middle, by basically having the correct noise model instead of like a Gaussian noise model, instead of removing cosmic rays or tracks or satellite tracks or things with different things. And so so I don't have a lot of time. I'm going to skip some of these things. You can do PSF deconvolution with these things. For example, here is just one case that I want to show you is that Alex is taking this galaxy from HST and then doing this combination of basically learning the noise model from the data and doing this PSF deconvolution and getting posterior samples that look like this. This is one posterior sample. This is another posterior sample. And then now it's gone to this galaxy has been also observed with JWST, and this is the JWST observation of this thing. So we can actually extract a lot of useful information out of these guys by just understanding well the noise model and the priors on these galaxies. So another random thing is that some of our work has gone into understanding also what is considered to be accurate. If you have some posterior and you say, this is my best guess, how do you quantify that's accurate? So this is a work that was published in ICMO with Pablo and Adam, who are two stellar postdocs in our group. And there's a package called CHARP. So if you want to know if your posteriors are accurate, you can just use that to quantify that. So just to give you a big picture idea is that my interest in all of this eventually comes down to Risa and others, they know dark matter substructures. So our goal is to be able to quantify the clumpiness of dark matter in lensing galaxies with these. So there's a kind of a big picture kind of program to have a lot of these pieces fit in together to be able to kind of do this hard measurement. Now, KIPAC, so I talked to a bunch of people when the pandemic kind of started, and I went to Montreal, did a lot of soul search, and I realized that I really miss KIPAC and the people and the environment here. And so I decided, hey, we can kind of build a fun community, the people here in Montreal. And fortunately, there's a lot to work with in Montreal. Montreal is a big AI hub in the world. There's lots of different incubators, research institutes, startups, big tech, and lots of different things. And one of the things that I'm a part of Mila is this big research institute in machine learning. So Mila has about 100 faculty members, about 1,000 researchers. It's like a big ocean of machine learning. And so there's a lot of machine learning happening, and there's a lot of astrophysicists in Montreal. But we decided to kind of make this connection, and we started this kind of new research institute called Ciela. And so it's a relatively small project. These are faculty members and admin. And Risa mentioned that 4 out of 7 faculty are actually Stanford people. And so the goal is to contribute to kind of breakthrough discoveries in astrophysics by focusing on data analysis and machine learning and figuring out how to do that. So there's like a bunch of different, programs that we've started doing in the spirit of like community building. Like we had this S2D conference 6 months ago for big optical surveys, astromatic summer school, and the physical sciences seminars. And then we do other things that I can't mention today, like I don't have time, like the Simon's Collaboration on Learning in the Universe that Laurence is leading at Montreal, and other things like software development, like Caustic package that is a differentiable kind of PyTorch-based strong lensing simulator. So I'll stop there and take your questions. Thank you.
Excellent. Questions, please raise your hand. Also on Zoom if you have questions.
This is super exciting stuff, Yashar. Thanks so much for sharing it. And I'll ask you technical questions later, but I wonder if you could say what things you've learned about getting astrophysicists and AI ML folks to work together effectively.
I think the most important thing is that I think you need people from the astrophysics side that really are almost at the cutting edge of ML so that they can make this communication and the connection. Because the ML people, they can work with anybody. They can just like, everybody wants them. And they don't have the patience to be like, come and learn about your baby astro problem. They don't want you to talk your problem and then they come solve it for you. They're interested in this being a hard ML problem, but then you need to speak their language. And so I think basically empowering a new generation of like people in the astro side that are almost ML, that they can talk that language, that they can publish in ML, papers, and making that connection is like one of the key things. And then of course there's like a lot of other things, and I'm just like I'm discovering that myself, figuring it out as we go along. So.
So in your example about, using diffusion models, you talked about modeling the PDF of all possible images.
Mm-hmm.
And in real life, it seems like the actual distribution function of whatever we're interested in is much, much lower dimensional. Like a lot of that PDF seems like it should be irrelevant in some way. Or like a lot of the dimensions should be irrelevant. Do you have any thoughts on that?
So in this particular case, for the analysis of a particular data, I mean, you don't want to train it on all the different images. You want to train it on the images that you consider to be coming from your prior. So in our case, if our prior is to be things of galaxy, we just want to throw images of galaxies. I don't want to train it on cats and dogs because then that's a whole different PDF. But I guess your point is that you don't really need to go to this super high dimensional space. So you can kind of like have some sort of lower dimensional representation of this. Is that what you mean?
Yeah, I'm thinking of like, like word embeddings where they embed them in like 500 dimensions, all words.
I mean, that's what VAEs were sort of, but they didn't work. So the amazing thing about these like diffusion and score-based models are that they actually work really well in these high dimensional spaces. And they're absolutely, like both the samples that are drawn out of them and the distribution that you learn is like absolutely indistinguishable from the images. Whereas like these lower dimensional kind of approaches like VAEs, for example, they never worked. And so a lot of people worked on that. They never managed to make them work. So you're right. So for certain problems, it's possible that there is lower dimensional kind of embeddings that kind of would work. But in general, it's just great to have this flexibility to be able to kind of learn any complex distribution because you don't know what you're going to have.
Okay, thanks.
I wonder if you want to say an extra word about H0 estimation, what you see as the future and the main challenges to bring this competitive with other methods.
The H0, I mean, all the experts, a lot of them are here in this room, probably like, I think from my perspective, the biggest problem is all the degeneracies. Some of them are fundamental degeneracies. And so we will be always to some degree, some sort of like model dependent. I think that there might be a universe in which, with the help of machine learning, we can actually tie in a lot of other observables, like full, kind of IFU imaging and dynamics of the galaxies, the environments and everything, to really reduce these things and so reduce our error bars. But But yeah, I think that's the main, which, you know, I think machine learning can help, but, you know, only to a certain degree.
Since Susan pushed you on H-naught, I'll push you on dark matter. Since we talked last, do you have new thoughts on how far we can push strong lensing down the mass function and what it will take to get there?
Invite me in a year. I think we're making absolutely a lot of progress in that front. It's really exciting. I think from an analysis perspective, finally, I think we know how to do this. And in terms of how far down we can kind of push it, I think we can push it down very far. I think the data is, we already have even the data that needs to be done. Of course, LCC and Euclid and these big surveys, they're going to be like amazing, so many more lenses. But we have been stuck on that for 20 years because of not knowing how to analyze the data. It's just a data analysis problem. And I think with a lot of these like different pieces, it's coming together. Look, I think it's one of the hardest problems I've ever heard of, not because I worked on it, because you have the weakest signal per lens. It's the weakest signal, extremely degenerate with a lot of other things. And so it is so easy to fool yourself and to get biased results. And so we definitely need to combine a lot of them. Yeah, I think we'll get there. I'm very optimistic now. I wasn't in 2017. When we started machine learning was when I just said, substructure doesn't work. This is just too hard. So let's just do something fun. And now I'm coming back to it. And I think we're getting there.
All right, fantastic. Any final burning questions? Or let's move on and thank Yashar again.